Welcome to section 7.2, and this one we are looking at integration techniques, anti-differentiation, and we're using the substitution method. We did look at substitution method last year, so hopefully some of this you'll start understanding a little bit better. The first example is an indefinite integral. It says if capital F, the function capital F, is any function such that the derivative of capital F is equal to little f of x, then I know that if I integrate little f of x, I will get an outcome or an antiderivative of big capital F of x. And you can do this very easily. I know you can. So probably should have had parentheses there. This will equal the integral of 2x squared divided by 2 plus sine of x plus some constant. And I'm going to switch that to be a negative so that I get negative cosine when I take the derivative. Simplifying, I'd have x squared minus sine of x plus c, the antiderivative. Just don't forget that it's that constant, and I should be able to check back if this is my big f of x. If I take the derivative of it, I should come back to this little f of x, shouldn't I? And I would get 2x minus cosine of x. The derivative of a constant is 0, and voila, we know we have the right answer. So for many of them, you can check your answers. Sometimes it gets not very pleasant. Power function, this is integration, adding a power back and then dividing by that new power. So add a power, divide by that new power. Recalling that if I have u to the negative 1, which would look like 1 over u, that integrates to natural log absolute value of u. All right, so I could think of this 5 being pulled out, x to the 7 dx. We are going to use the power rule and increase the power by 1, taking us to 8, divide by 8, plus c, so I end up with 5/8 x to the 8th plus c. This one, I would pull the 3 out front, and I have 1 over x dx. Now, 1 over x, I remember whose derivative is 1 over x? It's natural log, so I'd have natural log absolute value of x plus 3, or plus c. The 3 was in my head because I could show this as absolute value of x to the 3rd plus c, right? Because that power could come back up. Either inside or outside, it won't make any difference on that particular problem. Next, we've got, the trigonometric functions. Integrating, we should recognize all of these. Just think in reverse of taking a derivative and you will be fine. Exponentials, the integral of e to the u is e to the u, natural log of u. Now this one is tough. Here it is. We will show this when we get to the integration by parts section, which is in a few sections down the road in chapter 7. I'll show you how to get that answer. Right now you could memorize it, but I think in the AP they do not even expect you to have it memorized. A to the u, it has that correction factor underneath of natural log a, and then log base a, kind of the same thing. This is kind of a difficult one. I would say I think our gold sheets do not include that because that is not part of the AP standards. All right, substitution method. Finally, the one that we were kind of talking about. If I have an integral where I have this composite function, notice this is a composite function. Oopsie, can't write in the header there. This is a composite function. And then I have the derivative of that inner function. Notice derivative of the inside function. It is a prime candidate for u substitution. All right, so we will decide what to allow our u to substitute for, and then we'll integrate that u substitution with respect to u, and once we get done, we'll be in terms of u, but we'll swing it back, substitute back in our x values, and get it back into x's. So Here's my more complicated function. This would be the composite function, right? Now, the g of x would be located right up there. So this is g of x. Is there a g prime of x present? And for sure, there is an x squared. So it's decreasing by a power. I love this. This is setting us up for a very classic u substitution. So let u equal the x cubed. Then du would equal 3x squared dx. And I do a comparison. I don't have the x squared. I have 3 of them, so I'm going to divide by 3 or multiply by 1/3 and get 1/3 du equals x squared dx. Now I have everything I need to set up my substitution. The x squared dx gets substituted with a 1/3 du. Every single term that you work with must be substituted precisely. So I've taken care of those, and then I have e to the x cubed, but x cubed is the same thing as my u. So I'm going to write this as an e to the u. And you're probably like, boy, does that look like it's not in the right form. Nope. I'm going to move things around. I'm going to have 1/3 integral e to the u du. And most of the time, that's how I'm going to write it down when I'm doing that u substitution. I just wanted you to see all these parts that did substitute. The x squared dx came in with a 1/3 du. The e to the e raised to x cubed is replaced as e to the u. Now it makes more sense seeing it laid out in a little more normal fashion. The integral of e is itself, so it's an e to the u plus c. And then I don't want my answer to be left into u, so it is the subbing back. What is u equal? It's equal to x cubed plus c. Now, if you took the derivative, you could call this big capital F if you wanted to for the antiderivative. If you took the derivative, would you get back to this? Yes, you would, wouldn't you? You'd have the derivative of e is itself, and then I'd have to take the derivative of the inside function x cubed, and that would give me a 3x squared. A 3x squared times a 1/3 is going to be that x squared. So yeah, it works out very nicely. Next problem. Well, the more complicated function, the composite function, looks like it's there with that square root. So I would suggest let u equal the inside part, the g of x part. Let's see what its derivative is. It's a 2x dx. I need 6x dx. I think I'm going to go ahead and make it match. I'm going to multiply both sides by 3 because it's easy to do on this one. So I get 3 du equals 6x dx. Now I'm ready to come over and start substituting values. 6x dx is equal to a 3 du. So 3 du. I've taken care of those two terms. Now what I have remaining is the square root of 1 plus x squared, but 1 plus x squared is my u, and I'm going to make this raised to the 1/2 instead of looking at it as a radical. Easier if I'm using power rule to have the fractional exponent. So u to the add 1, I'd be at 3/2 multiplied by 2/3. Don't forget the c. And we are talking 2u to the 3/2 plus c. Substitute out our u with 1 plus x squared. Add our c. And we are done. I think I forgot something. I didn't like that. 3/2. I was doing the derivative in my head, and it's like, that's not enough. Yeah, I needed that 3/2. I missed that. Okay. Substitution method, once again, that's just the one we just did. I need to move forward. Oh, wow. This one doesn't look very cool. Cotan theta. Well, the derivative of cotan is negative cosecant squared. And I don't see any negative cosecant squared visible. So I think what I want to do is break cotan down into cosine theta over sine theta. Rewrite it. Use one of those trig substitutions. Now I have two functions. And normally I look to the denominator to pick the u. So I'm going to say u equals sine of theta, because when I was looking at this, they are kind of each other's own derivative, aren't they? So it made it a little harder to select your u. But normally let u come from the denominator if that's a possibility. Du would equal cosine theta. Oh, this is going to be so nice because there's cosine theta d theta. And this would be with respect to theta, so d theta there. And that's just a very clean substitution. So I'm going to have 1 over u for 1 over sine theta. And then cosine theta d theta gets replaced with du. This is natural log pattern, so it's natural log absolute value of u plus c. And let's get it back into terms of theta. So my u was sine theta plus c. Not bad. Okay, the next one, where are we at? Sine cubed. Ooh, sine cubed. So I could think of this as the integral of sine of x cubed dx, but that still isn't very helpful because I need, if I chose u to be sine, I need a cosine present. So what other things could I do? Well, there is a thing about sine squared. What if we broke away and do sine squared x times sine x dx? And then sine squared is the same thing as 1 minus cosine squared x sine x dx. Then let's distribute. So I'm going to end up with the integral of sine x minus sine, I'm going to lead with the cosine because that'll actually work better. Cosine squared x sine x dx. All we did there was a lot of pre-calc work. I'm just going to clear off some of this previous ink because I think that's what slows down the computer, is that it keeps trying to rewrite and save the file with all of that notation. All right, it's a hunch I have at least. All right, so we just did a lot of pre-calc work there. Now, with the addition or subtraction of integrals, I can break it into separate integrals. So that's what I'm going to do here. I'm going to call this the integral of sine x dx. That's an easy integral, minus the integral of cosine squared x sine x. And this particular one is going to be one that I want to use u substitution on. So for now, I'm going to get this one set. This would be negative cosine of x, wouldn't it? I could do a plus c, but I'm going to cover the plus c once I get done with the other integral. Minus. Now, let's set up a substitution on this. So cosine is my inner function. Squaring is the big outer function. So let's let the u equal cosine. Then du is equal to negative sine x dx. For now, I think I'm going to bring in, I could say I have the negative, but I'm going to be more careful and just say negative du equals sine x dx positive. All right, now into substitution here. So be minus the integral. Cosine is my u, so that'll be a u squared sine x dx is negative du. And now I can see that I could make these both positive here. Negative, negative makes positive. And I think we are ready to finish this. We would get negative cosine of x plus 1/3 u cubed plus c. There's the plus c we needed. Minus cosine x plus 1/3. We certainly don't want to leave our answer in mixed variables, do we? So we're swinging back into u's. Our u is cosine, so I'm going to have a cosine of x quantity cubed plus c. I could write it that way, or if you prefer, you could have written it with the third power in between cosine and x. All right. Next. It may happen that you get an extra x factor in the integrand. In that case, it is possible to solve the equation u equals g of x, but solve it in terms, or for x, so it'll be in terms of u. Watch what happens on this one. All right, we look at the more complicated function, and the inner part, the g of x, is 2x plus 1. So my gut feel from u substitution is let it be that inner function, and I get du is equal to 2 dx. Not super helpful. 1/2 du is equal to dx. Well, I would have this x, but then this would become u to the 1/2. Dx is a 1/2 du, isn't it? And everything's looking fine except for this fact I have x and everything else is in u's. That needs to be in a u as well. How do you do that? Well, let's take this statement, the u equals gx, and switch it into x equals. So if I do that, I would have what? U minus 1. I'm going to say 2x equals u minus 1, and then I need to divide by 2. So x equals 1/2 u minus 1. Now I can change out that. So I'm going to integrate. The x gets replaced with 1/2 u minus 1, u to the 1/2, and then I have the 1/2 du. Not very pretty the way I wrote it, but let's get things squished down. Let's do some simplifying. So this will be 1/2 times 1/2 makes this 1/4 u minus 1 u to the 1/2 times du. How do you integrate that? Easy. If I can get to a polynomial, I can integrate. So let's distribute on this. And that distributive would be u to the 3/2 minus u to the 1/2. Ooh, this is looking good. Du. Polynomials, love them. They're easy to integrate. We'll have 1/4 u raised to the 5/2 times a 2/5 minus u to the 3/2 multiplied by a 2/3, add c. We're almost done. We just need to get things back into terms of x's. So u was equal to 2x, 2x plus 1. I'm going to bring that down so I can see it. So switching this out, final answer, 1/4. I really should swing that through, shouldn't I? One step at a time. 2x plus 1 minus 2/3. Uh-oh, forgot my power, 5/2. Then 2x plus 1 to the 3/2 plus c. Now the final thing is to distribute to each of those terms to get this simplified as much as possible. And I'd have 2 over 20 gives me 1/10 2x plus 1 to the 5 halves minus 1/4 times 2/3 gives me 2/12, 1/6. 2x plus 1 to the 3 halves, add c. So, while you think when you start this one that it's not possible because the g of x does not have a derivative that's present, and you're like, dang it. But you can account for these extra x's. I think of these as a double substitution. So you'll hear me refer to them as a double sub. Are we getting close to the end? We got 2 to go. Oh, evaluating a definite integral. Definite integral meaning we have bounds, and indeed we do. We got the bounds from 0 to 2. I'm liking this because I'm looking at x squared minus 9 thinking its derivative is present. So I'm going to look to the denominator to set up my u. And let's let u equal x squared minus 9. Even though this is not a very complicated composite function, let's see if this technique of u substitution works out. So taking the derivative, I get 2x dx. I don't have 2 x's present. I only have 1, so that's a 1/2 du equals x dx. Previous page, I'm just going to erase the ink so we stay faster. Okay, that's perfect. Now, the bounds. Let's change the bounds. If I change the bounds, I must have to change the ink color. So bounds get changed. When x is 0, u would be 0 squared minus 9. That'll take us to negative 9. When x is 2, u would be 2 squared minus 9. So 4 minus 9 gives me negative 5. Sweet. Let's go set up our integral. New bounds. 0 is replaced with negative 9. 2 is replaced with negative 5. And I'm fine because I got my smallest number on top, or on the bottom, leading to my larger number up on top. So I don't have to do a flip over. Sometimes it can happen that you do end up flipping. 1 over u, because this is my u. Dx gets changed out with a 1/2 du. Squeeze in that 1/2 out front. Oh, do you recognize this? What is the integral of 1 over u? It is natural log, isn't it? So I have natural log, absolute value of u, evaluated from negative 9 up to negative 5. I'm going to leave my 1/2 way out front. Now, fundamental theorem of calculus kicks in. Start at the top. We'd have natural log of absolute value negative 5 minus natural log absolute value of negative 9. If you were tempted to write down 5 and 9 at those points, that's fine, because that's what I'm going to do next. I'm going to have natural log of 5 minus natural log of 9. And can I bring two logs together? Yes. That is that log property where I have the difference of logs becomes the quotients of logs. 5/9. And now if you really wanted to simplify, the 1/2 is really previously a power. So I could write it like that. Oh my gosh, the simplifying never ends, does it? I could write this as natural log square root 5 over 3. Yeah. Anywhere, I would say acceptable answers, anywhere along that path of those three. Excellent. I hope you followed that problem. Changing the bounds. Then I never have to change back to x's. All right, this one I think is here just because we should do a trig one. Now, my more complicated function definitely sits here, doesn't it? Whoops. Definitely there. Outer function, big outer function is the squaring. Inside function, g of x, is cosecant. Oh. But the derivative of cosecant is negative cosecant cotangent. How did I do that again? The derivative of cosecant is negative cosecant cotangent. Would I have that present? Yes, I would. I could go that route. My other thought was, what if I let u equal cotan, then the derivative of cotan is cosecant squared. This is a case where you really could do it either direction, and I think I'm going to let it u equal cotan. I just feel like that might be a little simpler. So let's let u equal cotan of theta. Take the derivative with respect to theta, so that would end up being a du d theta equals negative cosecant squared theta. Bring the d theta up and over, so I get du equals negative cosecant squared theta d theta. We really don't need the negative, so let's make it multiply both sides by negative. And now that'll be all fine, won't it? This will be u, and this will be negative du. Easy. Got that. We just need to change our bounds. All right, so I'm going to update this. Let's get the bound change going. The bounds. When theta equals pi over 4, u would be equal to, oh goodness, cotan of pi over 4. That would be cosine over sine. Same over same. Cotan's going to be 1. And then when theta is a pi over 2, u would equal cosine of pi over 2 divided by sine of pi over 2, which is a 0 over 1, which is 0. Oh, these bounds are tricky. Okay, let's do our substitution. Very carefully, pi over 4 converted to 1. Pi over 2 converts to 0. Do you see a problem? Yeah, we're going to have to flip that integral over. We'll deal with it in a moment. I was letting my cotan be my u. The cosecant squared theta d theta is a negative du. Now for the flip over, this becomes a positive integral 0 to 1 of u du. Oh, I like the integral. That becomes a 1/2 u squared evaluated from 0 to 1. Throwing in 1, I'd have 1/2 of 1 minus, throw in 0. I kept the 1/2 way out front, so I kind of did this number. And looks like our final answer is 1/2. Curious, did we make the mark? Woo! All right. You got to see a nice variety of problems here. Your homework is going to be a worksheet. It's loaded in Schoology, so you can work from there. This worksheet is not in your packet. It is a new one that I just found, so good luck with that.